All right. Um, we will continue our discussion in this buckling equation. Now we have already encountered the, the parameter of the slenderness ratio and the buckling loads and stuff like that. Now I think we're ready to to receive this graph, this something like a failure graph, and that's what we call the theoretical column curve. Okay, so meaning that the compression members or their strength is somehow affected by the slenderness. Okay, so we can write here along the x-axis the KL over R, and here we can write the critical buckling or critical loads. So that could be in buckling or yielding, FE. Okay, so meaning at some point, if you have a shorter or a stocking member and short, then your failure is this yielding line. But if you have a slender a column, then your failure would be this line. You have this buckling um, buckling strength or buckling curve. This one is the yielding. Okay, so meaning that our limiting value this uh, for this compression member is something like this. So beyond, I mean, under this curve, you are safe, but beyond this curve, you actually fail. But along, or let's say in this region, at some point of at some, let's say, limiting values right here, then if you go beyond this critical value, then you fail by yielding. Whereas here, if you have a slender element, if you if you go beyond this value, you fail by buckling. However, take note that this is just a theoretical a column curve. In actual columns, uh, you'll actually get a different curve, and it's below this line, uh, below these yielding lines, and also something like this. Okay, we can just use this one. Okay, now this curve is referred to as the um, AISC column curve. Okay, so actual columns, they're actually based here. Theoretical columns, this is the curve. We'll get into the details of this AISC column curve later, but for now, we'll now move our discussion to derivations and the code provisions. Okay, so as usual, when we talk about the derivations and code provisions, we talk about limit states. That's very typical for a steel structure. For compression members, we have three limit states for now, and that's gonna be the flexural buckling. This one, another one is torsional buckling. So under the applied compressive forces, instead um, of buckling, you're actually twisting. So that's the uh, torsional buckling. And the third one is the flexural torsional buckling. So it's just the combination of the two. Okay, so this one, the flexural buckling, this is um, what we have discussed earlier. This is basically the um, let's write it here. Basically, the Euler buckling. So if you have a slender column, long and slender column, then under the compressive force, it fails. It can fail this way, the flexural buckling. Now this one, the torsional buckling, is a type of failure caused by twisting about the longitudinal axis of the member. So, for example, we have here. So at some values of these loads, probably, or could be the type of the cross section can also be um, can also matter. And if we, I mean, under this load, then this one actually deforms in a twisting manner. So okay, so if you, okay, let me draw the top view. So let's say this is the original configuration, but under compressive forces, it actually twists something like this. Okay, so that's the torsional buckling, and the third one is basically the combination of the two. So it twists and it bends. All right. There are actually certain types of shapes. We have mentioned already doubly symmetric. We have also singly symmetric. What it means is that, for example, a W shape, it's actually symmetric on, if you try to look at this y-axis, along the y-axis, it's symmetrical, and along the x-axis, that's there, it's also symmetrical. So meaning that it is a doubly symmetric. For this one, for the channels, it's just symmetric in this axis, but here it's not. And this angle, uh, they're not symmetric at all, except that along this axis probably. But that's the point here. For some shapes, then what's I mean, the governing limit states could be probably just these flexural members. I mean, flexural buckling. But for some shapes, probably this one is. I mean, uh, they're probably more prone to this type of the limit states. Okay, but in our lecture, we'll just focus on the flexural buckling, and we'll only focus our discussion in this doubly symmetric shapes. Okay, so now recall that I said there's three limit states, but that's just uh, for a moment, because there's actually another limit state. So we can just write it for limit states, because there's another type of limit states, and that's called the local local buckling. Okay, so this local buckling is basically a buckling of the, or a buckling at the local portion. So compare that to the three limb states that we did. That refers to the general buckling. This one, under the let's say under these compression forces, it is probably possible, or it is also possible that uh, before the general buckling occurs, it is possible that, let's say, a portion of this flange buckles, or probably a portion of the web buckles. Okay, so something like this under the compressive forces. So that's what we call the local buckling. For the general buckling, it's like this. It's buckling in a general way. Okay, but this one, it buckles on this either the flanges or the webs or other elements. So now the question is, how can this happen? How can this local buckling happen? This happens. Uh, this happen when the flanges or webs, or let's just say elements, are thin enough. Okay, are thin enough that they buckle. Before the overall buckling happens. Okay, so meaning if these elements are slenders, then it is possible that they buckle before the overall buckling can happen, right? So meaning that there's actually a factor of um, the slenderness of these elements also comes into play in determining this local buckling, or let's say the strength of the compression members. Okay, so we have to check this local buckling as well. So this gives rise to the concept um, of the width to thickness ratio, and is denoted by this alpha. What is this? Lambda. Okay, so that's the parameter. Referred to as, sometimes referred to as slenderness or relative thickness. Relative thickness. So how do we compute this? The idea with this is, let's say we have this graph or something like a line, and let's say this is a measure of slenderness, and let's say we have a low slenderness value and we have high slenderness value. Now for low slenderness value, then it means it is a thick element, but for high slenderness value we have a very thin element. Okay, so how do we know if our element, and take note again, when I say element, I'm referring to the flanges or the webs or the legs of an angle bar, for example. Okay, so how do we know if these elements are slender or not? There's actually a limiting value right here. So this value is denoted as lambda sub r, and there's another value right here denoted as lambda sub p. But this slenderness, if we're just dealing with compression members, then this one is this one comes into play, the lambda sub r. But this one, if we're dealing with flexural members, actually y sub p and y sub r for both flexural members, and that's our topic next week. But for compression members, we'll just deal with um, lambda sub r. The point here, they are just actually the limiting values. Okay, so how do we know this? How do we know the value of this lambda sub r? We go to the table. Table regarding limiting width to thickness ratio. By the way, um, this this lambda sub r is a. Well, let me specify this first. Okay, so if you have a slenderness greater than this lambda sub r, then meaning that that the element is a slender element, but less than uh, lambda sub r, but greater than lambda sub p, you have a, I think this is non-compact section. Okay, it's referred to that non-compact section, and below y sub p you have a compact section or compact elements. Okay, so again, as I've said that for compression members, we only have this limiting values, lambda sub r. Therefore, we can just have either slender or not slender. This this term right here, compact or non-compact, they'll come into play when we're dealing with the flexural members. So for now, this we'll only have this lambda sub r. It's just the limiting value for non-compact sections. This is the limiting value for compact sections, or you can just we can just say probably limiting value for the slender sections. Okay, so now let's go back to this what I mentioned about this table. There is a table about the limiting width to thickness ratio, and it's actually a long list of tables for both for both flexural or members under flexure and compression. But I have provided in our lecture handout a table that only correspond to what we need in this lecture. And we have this. Okay, so we have here, let's say the case, and this one is description of element. And this one is our slenderness. This is lambda sub p, and then this one is lambda sub r. And this is the example. Now we have a case number 3. Our case number 3 is for flanges of rolled I-shaped sections. Okay, and then other conditions as well. You can just read that in our lecture handouts. And it says here that our equation for the slenderness is B all over T. Now, what is this B over T? There is a figure right here. Example, we have I-shaped sections. It says here that the B is this B. And this one is the thickness. Okay, so that's the nomenclatures. And you notice that for lambda sub p, it says it's not available. And this one, lambda sub r, this is 0.56 square root of e all over fy. So that's how you're going to check the limiting values. Okay, so and also take note, this is just case number 3 because I only included the selected cases. And for the web, it says here uniform compression in webs of I-shape sections. So here we have let's draw again this one. and it says here the H. So this is the H. Uh, by the way, our equation here is H over T sub W. So this is our H, and then this is our thickness of the web, T sub W. And this Y sub P is, it states not applicable. And this was not 1.49 square root of E all over Fy. Okay, so I also included another section right here. This is it's a circular hollow section, and you can just read that in our lecture handouts. Okay, so this is how we are going to determine this slenderness. So once it is greater than this lambda sub r, then it is slender, and therefore it is going to have a local buckling. And this this will also determine the equations that we will use for the compression, for the strength of the compression members. So here in our lecture, we'll only consider the strength, or we'll only consider or tackle the sections that has a non-slender elements. Okay, this one, no. So that we will not have to worry about this local buckling. Okay, there's also a term right here. You would notice that there's unstiffened elements, and here we have stiffened elements. Okay, what it means is that these unstiffened elements only, we can say only one end is constrained, for example, and this one, both ends are constrained. Okay, so for example, this I-shaped section, this element right here, this element, this is example of unstiffened elements. Why? Because only this portion is constrained, but this web right here, this is what we call, this is an example of stiffened element. Okay, so for stiffened elements and unstiffened element, unstiffened element, we have this equation of lambda is just equal to, for unstiffened, it is B all over D. Okay, and what is this B? What is this distance B right here? From the table, we only have this, the width of the flange, BF. So meaning that our B is BF all over 2 divided by the thickness of the flange. Okay, so that's going to be T sub F. And for the stiffened elements, we have this lambda is equal to H all over T sub W. Okay, and our limiting values can be found from this table. We just substitute the value of modulus, Young's modulus, and this yield strength. You take the square root and multiply that to this constant here, and you compare that to the value. Okay, so now let's talk about the strength of compression members. All right. Okay, so let's write the strength of compression members. Okay, the code actually says, or that the nominal compressive strength, Pn, shall be the lowest um, value obtained to the three overall buckling state. Okay, so recall we have flexural buckling, torsional buckling, and flexural torsional buckling. However, there is a provision that it says for doubly symmetric and singly symmetric members, the limit state. Okay, I'll just write here dot dot dot. So it says that for doubly symmetric members, um, the limit state of flexural buckling is applicable. Is applicable. And except that if the unbraced length, for example, we have this compression member, there is a braced length. Let's say this is a beam, for example, and then another beam, then another, or let's say a base plate right here. So if this braced length, let's just denote it as L sub B. Now, if there's a brace length, I mean, if the brace length is greater than the torsional unbraced length, then the torsional buckling limit also applies. Okay, so the longer you have, the longer the unbraced length is, then it's prone to the torsional buckling. So it can twist. But in this course, we'll only consider this flexural buckling only, the strength on this flexural buckling only, and um, without slender elements. Okay, and take note that our reduction factor is equal to 0.9. Okay, that's our reduction factor for compression members. So V sub C. And also, there's also tables that you can find that, for example, a um, doubly symmetric shape and this round shape. What governs here the limit states? It says that we have flexural buckling and torsional buckling. But for this one, this is flexural buckling, and this only applies um, for this example for this type of shapes, but without slender elements. So that's the importance actually of determining the slenderness. Okay, so if we have a section that has no slender elements, and let's say we're only determining the strength in terms of these flexural buckling, um, flexural buckling limit states, then our equation would be Pn is equal to FCR times AG. Okay, so again, if we have a section um, without without slender elements, take note, slender elements, and we are determining this flexural buckling capacity, then our equation would be this one. Pn, P sub n is equal to F, the critical stress, and times the gross area. So this one is the nominal compressive strength. All right. I guess I'll continue this this discussion in the next video.